So let me go ahead now and give you an explicit step-by-step example of how this process works. So we're going to design a bandpass filter between the frequency range that you see here. We're going to choose our Chebyshev approximation, and we're going to choose an nth equal 5 order filter. We'll also define the ripple by requiring that the return loss in the passband never exceeds 20 dBs. The geometry dimensions are also given in this figure. So we're going to basically use a transmission line. If you go through the calculations, and it's not the point here of this lecture, but if you go through the calculations of this, you'll find out that you need a 5.47 millimeter width to basically get a transmission line of 50 ohms. So this is what we'll assume that we need. And this is for an epsilon r of 2.22 for a duroid substrate. The other calculation you need is basically the equivalent lambda g. So that's the guided wavelength. So lambda g is basically nothing else but lambda naught, the free space wavelength, divided by the effective dielectric constant, which is practically 1. And so essentially you basically have almost free space wavelength in this calculation. So this is a table that basically summarizes all the numbers that you will need to run. And so as I mentioned before, you have the Chebyshev polynomial. You have that the n is equal 5, which means that you will immediately have all the j parameters that you need for your solution. Once you have all the j parameters, you will basically be able to find all the j's, meaning the inverter values, and these are the explicit values that you will have. Once you have those inverter values, you can immediately apply this equation here and find out the unknown susceptance BB, which is basically what this column gives you. And once you have this susceptance BB, you can basically find the gaps, as you can see here, for the specific equation we need and the specific implementation we need. So as far as the gaps are concerned, it's just nothing more but just marching through a set of equations now to basically get them. And these are all the gaps that you need between the different resonators. It's actually interesting to look at that the structure is basically symmetric, as you would have expected to be, and of course is reciprocal as well. Now, once we know the gaps, the last step of this design is to basically find out the true lengths of the resonators. Remember that the resonators will be approximately half a wavelength. So we have already calculated the lambda g. So approximately we're looking for lambda g by 2. But the issue is that we have to take into account those negative lengths. So those negative lengths are related to the fact that this angle here will be negative. And so we will compute all the negative lengths that we have and then subtract them from lambda g by 2. And so that means that most of the resonators will be close to lambda g by 2, but not exactly. So you can see, for example, all of the lengths here are about the same, but not really exactly the same because these negative lengths do change. So if you go through this exercise, then you have all the explicit numbers that you need for your layout. Essentially, this is the layout here that you would need to put down on a PC board or some other implementation technology. All the lengths here are basically given. All the gaps are basically given. You lay this thing down, and assuming everything works well, you will get this ideal response that you will see right here. Now, let me make a few comments here so you can have a good anticipation of what might happen in real life if you go ahead and you do this process. So the first thing I'd like to to remind you is that this is a narrowband synthesis approximation. So we have assumed that the J inverters work from basically DC to light, but that's not true. So essentially what that means is that if you move really far away from your resonance, you're not going to basically follow this ideal response that you see here. The second thing you should be aware of is that currently we're using an approximation and relatively simple models to account essentially for the interresonator coupling, which is of course is related to the J. In real life, when you lay this thing down, the exact layout will have uncertainties, it will have fabrication errors, and it's not going to work as ideally as you will see it here. Those type of things will show essentially as errors in the curve. For example, you might notice that some of the reflection zeros here will be misplaced, and you might have a little bit too high of reflection at some point. So that means that now you have to basically fix this and bring it down. How do you fix this and bring it down? Well, you need to go ahead and tweak things. So you may have to play with the gap a little bit, or you may have to play with the lengths a little bit to basically optimize. Thank God, all modern tools essentially include optimizers. And so as long as you start with values that are pretty close to reality, like the ones that you see here, any optimizer in any modern tool, like the ADS we're using for this class, can essentially do this work for you very quickly. So the last step in real life is to basically do this final tweaking based on the layout. And the more accurate your tool, the better your result will be. For example, it's one thing to demonstrate this and simulate it with an ADS circuit level simulation. It's even better to go with an ADS or an equivalent tool like HFSS for a layout-based simulation where the couplings will be computed from the true electromagnetic field that you have here. Now, of course, then finally you'll have to make the circuit. You'll have to fabricate things. As I mentioned, there will be likely fabrication errors. So as the very last step, there might be some trimming that you need to do right on the layout. So it depends really how accurately you want to hit the response of your filter. But if you want to really hit the specs without any unknowns, it may take a couple of iterations to make your filter and basically trim it. Now imagine that this job is a little bit harder if you need to produce a few hundred or worse, a few million of those. And so in those cases, you need to understand your tolerances pretty well. And then that means you need to define tolerances in the specs that you can live with.